All right, guys, in this lesson, we are going to start using the derivative to tell us some things about our original function. So today's lesson is about extrema on an interval. Okay, so the definition of an extrema is that it's a maximum or a minimum. So you've heard those words before. We're going to use some calculus to determine where those maximums and minimums occur and what the values of them are. All right, so the definition of an extrema is that if f is defined on an interval I, which contains a value c, then f of c is the minimum of f if for every value in the interval, f of c is less than f of x for all x in the interval. All right, and then f of c is the maximum if f of c is greater than f of x for all x's in the interval. Okay, so this definition is referring to what we call the absolute maximum and minimum. You can also use the word global maximum minimum. Those words are interchangeable. You would see both of them depending on what textbook you're reading, depending on if it's an AP exam question. I've seen AP exam questions use both. I think absolute is more in trend right now than global is, but you should be aware of both of those words. All right, and then we also have what are called relative extrema. So again, we're on an open interval, which contains c, and f of c is a maximum. Then c f of c is called a relative maximum if you can say, c f of c is called a relative maximum of f, or you can say that f has a relative maximum at c f of c. Okay, so what this means is like basically if you have a big interval, but if you condense that down and just look at a small part of the graph, is there a little maximum in that small part of the graph? That would be a relative maximum. All right, so we're not looking at the whole interval, we're just looking at a part of the interval. Okay, and then same deal for the minimum. If you look at a part of the interval and you have a small minimum there in that little part, then we call that a relative minimum. There's another word for this as well. Instead of relative, you might hear it called a local maximum or local minimum. All right, so let's look at this graph over here. So in the figure on the right, we have a graph on the interval from -2 to +4. All right, so what that means, it's a closed interval because we have the square bracket. So we have a closed circle on the end here, and we have a closed circle on the end right there. All right, so f has an absolute maximum. So absolute just means the highest point of the whole graph. So I would say the absolute maximum is at x equals 4. All right, I'm going to add a little bit here. The absolute max is... So if they ask for where it's at, you want the x value. If they ask for what it is, you want the y value. So the absolute maximum is 21. All right, f has an absolute minimum at -2. Absolute min is -15. F has a relative maximum. All right, so now we're going to zoom in on a graph. And so we're going to zoom in on an open interval right there. Okay, so we zoom in and we just look at this part of the graph. And so within this part of the graph, we do have a maximum right there. So that would be called a relative maximum. And the relative maximum is at 0. Relative max is 5. All right, and then if you zoom in on a different open interval right here, then you can see that it approaches a minimum, or it has a minimum in that open interval. Okay, so that relative minimum is at 2, and the relative minimum is 1. All right, so that's basically the 4 things that we're going to be looking at, and we're going to use calculus to determine all of those values. All right, so this is the definition of a critical number or a critical point. We use those kind of interchangeably as well. So f is defined at c, then f prime of c is equal to 0, or f is not differentiable at c. So either f prime is equal to 0 or f prime is undefined. All right, I'm going to write that under here, or f prime is undefined. Sorry, I got to spell correctly here. All right, then that means that c is a critical number of f, and the point c, f of c, is a critical point. All right, theorem, relative extrema occur only at critical numbers. So what you'll be finding here is all the values where a relative extrema could occur, Just because it's a critical number does not mean it's automatically a relative extrema, but a relative extrema will never occur at any other point other than a critical point. All right. So one more thing to point out here with this definition. A lot of people automatically find where f prime is undefined, and they include that in their critical numbers, their list of critical numbers. But you do have to remember that f must be defined there. Okay, so if you find that f prime is undefined, it could be because f was also undefined, like a vertical asymptote situation or a hole in the graph. So you do want to make sure that the critical points you find are defined on the original function. All right, don't zoom in and focus too much on the derivative. Think of the whole picture. Okay, so we have some examples here. All right, we're going to name the maximum minimum points if that's possible. All right, so this has a minimum at. All right, so lowest point, minimum is right here. Minimum is at 0, x equals 0. Minimum is 1. Maximum at, highest point, right there, 2. Maximum is, what is that, 5? 1, 2, 3, 4, 5. All right, minimum at. Same graph basically other than this hole in the graph. And yeah, I think I have the same minimum. Minimum at 0 is 1. Maximum at, all right, here we run into a problem. Okay, so this is where our maximum would have been, but it's undefined. It's an open circle. So, like, can we say that there's a maximum point? Well, you could say, well, what about that point right underneath it? Maybe it's that one, 4.9. Okay, the problem with that is I can always make a point a little bit closer, 4.99, and then a little bit closer, 4.999. All right, and there's an infinite number of points in between whatever point I say and 5. There, we can always fit another point inside there. So if you're where your maximum would have been, if it's undefined, then you have no maximum. There is none. All right, so we're going to have that same situation over here. So where our minimum would have been is now undefined, so we will not have a minimum. And then our maximum is back to being a closed circle, so our maximum is maximum's at 2 and is 5. So what conditions are necessary to guarantee that there will be a maximum or a minimum? All right, so sorry, I had to pause there for a second. All right, what conditions are necessary to guarantee that there will be a maximum and a minimum? All right, well, what happened on these two for us to not have one? All right, well, we had a discontinuity, a hole in the graph. So what conditions are necessary? What did this one have that these two did not have? The function must be continuous on a closed interval. Okay, that closed is important because look at letter B. It is continuous for an open interval. The only place where there's a discontinuity is on that endpoint right there. Okay, but that made a big problem for us when we were trying to find a maximum. So it has to be continuous on a closed interval to be able to have a maximum and a minimum. Okay, and I do want to clarify that this is an absolute. Same thing here. Okay, so you can still have relative maximums and minimums on an open interval. Okay, but to have an absolute maximum or an absolute minimum, your function must be continuous on a closed interval to guarantee that there will be ones. Okay, now there could still be like this one was not continuous on a closed interval, but it still had a minimum that we could find. Okay, but to guarantee that there's both, a function must be continuous on a closed interval. All right, let's turn it over. Okay, so that is the extreme value theorem. We just discovered what the extreme value theorem is. Okay, so here it is just stated out for you. If f is continuous on a closed interval a to b, then f attains an absolute maximum value of f of c or an absolute minimum value of f of d for some numbers c and d in an interval a to b. All right, so what this is really saying, all right, that's the fancy math way of saying it. So what this is really saying is that if f is continuous on a to b, closed interval, then f must have an absolute max and and absolute min. All right, that's what this theorem says. So if they give you a function which is continuous on a closed interval, then f must have an absolute maximum and f must have an absolute minimum, and you should be able to find them. All right, so here is how we find them. We're going to use what's called the candidates test. There is another way to do it. I will show you that other way on certain problems where it is useful, but I always prefer the candidates test for this. All right, anytime you're finding an absolute maximum or an absolute minimum, you want to do the candidates test. Okay, so you will be given a function. They will give you a closed interval for that function. Okay, so that's what you're looking for. That has to be given to you. All right, this function needs to be a continuous function on that closed interval as well. All right, so what you do once you have all that is you find the derivative and the critical numbers, which remember critical numbers is where f prime equals 0 or f prime undefined. Okay, you evaluate each critical number in A to B. All right, that means you plug them into F. Plug into F. All right, you evaluate at each endpoint, f of A and f of B. One of these values is a minimum, and the greatest value is the maximum. The least of these values is minimum, and the greatest is the maximum. So you're going to be making a table. You're going to have a table of x and f of x. All right, you're going to have some values. You're going to have A, you're going to have critical point 1, critical point 2, and you'll have B. All right, you plug all those into the function. All right, and then you'll have like big, medium, small. Smallest one is your minimum. Biggest one is your maximum. That's the candidates test. All right, let's do it. So we have a function, f of x equals 3x squared minus 24x minus 1. Okay, the function must be a continuous function on a closed interval from -1 to 5. So I'm just going to say that f of x is a polynomial and is continuous everywhere. So we don't even need to worry about continuity on this specific interval because this function is continuous everywhere. Okay, so we are going to find the derivative. F prime of x is equal to 6x minus 24. We are going to set our derivative equal to 0. And we get a critical point at x equals 4. Okay, so once you found your critical point, or points, there could definitely be multiple critical points. We only have one on this one, then we make a table. In our table, we're going to include our critical point and both endpoints. -1, 4, and 5. I like to write them in order. Okay, once you've identified the x values, so these are the only possibilities of where an absolute maximum or an absolute minimum could occur. It's going to be at one of these 3 points. Okay, and the way we find which one's which is you plug them into the original function. All right, so -1 squared is 1. Times 3 is 3. So I'm going to write out a little work here. That's 3. -1 times -24 is positive 24. And then minus 1. So that's 27 minus 1, which is 26. All right, 4 squared is 16. Times 3 is 48. Minus 4 times 24 is 96. Minus 1. So 48 minus 96 is -48. And then minus 1 is -49. Plug in 5. 5 squared is 25. Times 3 is 75. 5 times 24 is -120. And then minus 1. All right, 75 minus 120 is -45. Minus 1 is -46. All right, and so we are going to identify our absolute maximum. Let's see here. Can't decide what color I want. Let's do that one. Absolute max. Okay, you can write it a couple different ways. So absolute max is the y value, biggest one, 26, occurs at x equals -1. And then absolute min is smallest number, -49. That occurs at x equals 4. Okay, I think it's probably also okay if you just label it absolute max. and then write the point, negative 126, and absolute min for negative 49. All right, I'm partial to this because I like for you to identify that you know that the maximum is the y value and it occurs at the x value. Okay, so that shows up on multiple choice questions a lot where they ask you, sometimes they ask you where does the maximum occur, and sometimes they ask you what the maximum is. And so I always want y'all to be thinking about how it is the y value and it occurs at the x value. Okay, so I'm going to have us write it that way every time. All right, I would encourage you to try letter B on your own, and then unpause the video and see how you did. All right, I'm going to be a little lazy, and I'm just going to draw an arrow from this. This is also a polynomial, and it is continuous everywhere. So we've got the continuity. All right, let's find our derivative and do our work. So f prime of x is equal to 18x squared minus 24x cubed. All right, I can factor that. I'll just do it this way. I can take out, I think, a 6 and an x squared. And that'll leave me with a 3 minus 4x. All right, so that is equal to 0. Really, we have two different ones. We have 6x squared is equal to 0, and we have 3 minus 4x is equal to 0. So I get x equals 0 from this one. And let's see, subtract 3, divide by negative 4. So x equals 3/4. Yeah, I think we're good with that. All right, so we have our critical point, so let's make our table. All right, so I'm going to include my endpoints, negative 1, 0, 3/4, and 2. We're going to plug all these into our function and figure out our maximum minimum. Okay, so we have negative 1, so that's going to be negative 6. It's going to be another negative 6, and then plus 5. Negative 12 plus 5 is negative 7. Plug in 0, it's going to 0 out those two, and we're left with 5. 3/4 is going to be tough. I'm going to do that one last. All right, plug in 2, cubed is 8, times 6 is 48. 2 to the 4th power is 16, times 6, that's 60, that's 96. So minus 96, and then plus 5. 48 minus 96, we have that same one over here, that's interesting. Negative 48, plus 5 is negative 43. All right, 3/4, I'm going to have to write down a little work here. So 6 times 3/4 cubed minus 6 times 3/4 to the 4th power plus 5. All right, so this is 6 times 27 over 64. This is 6 times 81 over 128. Ooh, I feel like that's wrong. No, yeah, it's 256. It's 64 multiplied by 4 again. So 256 plus 5. All right, we need to multiply by 6 on top here. So that's 120 plus 42 is 162. 480 plus 6 is 486. And then we need to get a common denominator. So I'm going to multiply by 4 over 4. 400, 240, that's 648. 648 over 256 minus 486 over 256. Then multiply by 256 over 256. It's 1,000 plus 250, so 1250 plus 30 is 1280. All right. This is a lot to do without a calculator, so I would highly doubt that this would be on a non-calculator part of the test, but I don't have my calculator out in front of me, so that's why I'm doing it this way. Okay, I'm going to add the two positive numbers first, so that's 18. Here, we'll just do it this way. 1280, 648, that's 8, that's 2, that's 9, that's 1, and then we're going to subtract 486. That's 2 Take 1 from the 9. 12 minus 8 is 4. 8 minus 4 is 4. 1442 over 256. All right, I'm done. I know I can reduce, but that's good enough. Okay, so we need to identify the absolute maximum, absolute minimum. Absolute minimum is super easy. Negative number, the biggest negative number. So absolute min is negative 43 at x equals 2. Absolute max is, all right, so I know it's not the negative number, so it's one of these two. And I'm thinking like, it's hard, but look what we just did. We just turned 5 into a number over 256. So this is 5 right here. 1280 over 256, and this number is 1442 over 256. That's the biggest number. So our max is 1442 over 256, and that occurs at x equals 3/4. All right, let's check out this next one. So we have, we can call this a polynomial because it does have a radical in it with a cube root here, but it is a continuous function because it's an odd exponent, the odd part being the denominator. And the rest is just a polynomial. So you can kind of think of it as like a cube root function, which is continuous, and a linear function, which is also continuous. And subtracting two continuous functions is a continuous function. All right. So f of x is continuous on our closed interval. All right. I'm not going to write it, but we talked about it. Okay. Take the derivative. F prime of x is equal to, multiply by 2/3, you get 2x, subtract 1 from the exponent, negative 1/3. Negative 2, and then plus 1 goes to 0. All right, so our derivative, I'm going to change that to a positive exponent by moving it down 2 over x to the 1/3 minus 2. All right, so we need to do two things. First of all, I see I now have an x in the denominator. Anytime I see an x in the denominator, I immediately start thinking about what numbers would make this undefined. Okay, if I put in 0 for x, that would make it undefined. So f prime is undefined at x equals 0. All right, so that's a critical point because our original function is not undefined at x equals 0. I get a number if I plug in 0 up here. Okay, so that's going to be a critical point. And then I also need to take my function and set it equal to 0. So 2 over x to the 1/3 minus 2 is equal to 0. All right, we're going to add 2. I'm going to multiply by the denominator. I'm going to divide by 2. And then I'm going to cube both sides. And so I end up getting x is equal to 1. All right, so I have a critical point at 0, I have a critical point at 1, and then I have my endpoints. So let's make our table. So negative 1, and then 0, and then positive 1, and 8. All right, we're going to plug all these into the original function. So if I plug in negative 1 squared is positive 1, cube root of 1 is 1, and then multiply by 3 is 3. So that's 3. Negative 1 times negative 2 is positive 2 plus 1, which is equal to 6. If I plug in 0, that's going to be 0, 0, and plus 1. So that's 1. If I plug in 1, I'm going to get 3 minus 2, which is 1, plus 1, which is 2. If I plug in 8, all right, cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12. Negative 2 times 8 is negative 16 plus 1. So that's negative 4 plus 1, which is negative 3. So my absolute min is negative 3 at x equals 8. And my absolute max is 6 at x equals negative 1. All right, last one. So these functions are continuous. Sine is a continuous function. Cosine is a continuous function. If you add two continuous functions together, you get another continuous function. All right, so we can take the derivative. F prime of x is equal to 2 sine x cosine x. We're doing the chain rule there. So 2, keep the inside part the same, subtract 1 from the exponent, you get 1, and then you multiply by the derivative of the inside, which is cosine. All right, and then the derivative of cosine is negative sine, so minus sine x. All right, we're going to set this equal to 0. We can do some factoring. We can take out a sine x, and that'll leave me with a 2 cosine x minus 1. Then we set each part equal to 0. So this one, I unit circle, and I get x equals 0, and pi, and 2 pi. And over here, I get cosine x is equal to 1/2. So x is equal to pi over 3 and 5 pi over 3. I think we're good there. Yeah. Okay. So we have 5 values. It turns out that our endpoints were also part of our critical point list. So we got a little bit of overlap there, which definitely happens sometimes, as you can see. And so we will just put these, and again, I like putting them in order. You don't have to put them in order, but it's nice to kind of keep things in an order. So 0, and then pi over 3 would be next, and then we have our pi and our 5 pi over 3, and then 2 pi to finish it up. Okay, so we're plugging these into our original function. Sine of 0 is 0. Cosine of 0 is 1. So that's 0 plus 1. All right, sine of pi over 3 is square root of 3 over 2. And then you have to square that. And then cosine of pi over 3 is 1/2. All right, so this is 3 over 4 plus 2 over 4, which is equal to 5 over 4. Sine of pi is 0. Cosine of pi is negative 1. Sine of 5 pi over 3 is negative square root of 3 over 2, but it's sine squared, so we're squaring that. Cosine of 5 pi over 3 is 1/2. So since I square this, I do get a positive 3 over 4 plus 2 over 4 is 5 over 4. And then sine of 2 pi is 0. Cosine of 2 pi is 1. All right, so on this one, our absolute min is just the one negative number is negative 1, and that occurs at x equals pi. And then our absolute max is, okay, and we actually have 2 answers here. 5/4 is a little bit bigger than 1, so 5/4 is our answer, 5/4. And this occurs at 2 different places. So we're going to have 2 ats here, at x equals pi over 3 and x equals 5 pi over 3. So your absolute maximum or absolute minimum could occur at more than one location. That's definitely okay, and that happens all the time with trig functions because of how they work. They oscillate, and they're going to hit those same peaks and the same valleys over and over again. It just depends on what your interval has closed in for you. All right, so that is how to find absolute maximums and minimums. Hope you enjoyed that lesson, and I'll see you on the next one.